problem is there are a lot of things that you need to move from one place to the other, and that's not the direction that they want to go. There are a lot of things that you need to shove molecules into a cell when there's already more in there than there was before. Um, or you want to get things out of the cell when there's already more outside the cell. The only way to make things go against the gradient, meaning from low to high concentration, is you got to pay for it. Primary active transport is powering special pumps in the membrane with ATP. Think of ATP like a battery operated device. You can go out to the store, you can buy batteries, you can stockpile them, you can have an entire closet full of batteries so that when the power goes out, you can put them into your little battery operated fan and use that to, turn the fan on in the middle of a power outage. No batteries, no fan. All right. As long as you have batteries, you can turn the fan on everywhere you want. You can blow air wherever you want to, as long as you are willing to provide power the whole time. The second you take a battery out, it shuts down. The second you get rid of ATP, these pumps shut down. They will pump in any direction, and they will also pump at any speed that you want, as long as you are willing to pay the price. So, oops, hang on. So you can pump things faster by using up more ATP. You can pump it slower by using less. You can totally stop it by not using any ATP. But the key is that you need ATP that you've already made, that you already have on hand. Okay, when the power goes out, that is not the time to try to build a battery. You need them already. The best example of this is the sodium potassium pump. You will see this ad nauseum when you get to the nerves, but this is how nerves work. And when I talked about the electrical chemical gradient in the sodium and potassium, this is what makes it. They pump 2 potassium ions into the cell, and then at the same time pump 3 sodiums out. That's an imbalance. If you pump 3 positively charged sodiums out and 2 positively charged potassiums in, you have a sodium concentration difference. There's more sodium outside than in. There's more potassium in than out. And you also have an electrical difference because the outside has more positive charges because it got 3 positively charged things when the inside only got 2 positively charged things. These things are so common in your cells that 40% of the calories you eat, now this does not count exercise. As soon as you get up and move and start using muscles are the most expensive things that you have, which is why that's what you use to burn extra calories. But like in your sleep, basically, 40% of all the calories that you've eaten are going to just running sodium potassium pumps in your cell membranes. Your nerves are absolutely loaded with them, which is why your brain is the most expensive little bag of jelly that you've got. That uses, just your brain uses 20% of your caloric intake resting. Again, take exercise out of the thing, but your little brain uses 20% of your calories because these pumps are not cheap and they must be running 24/7 for nerves to be able to work. The nice part of this is that they, can pump things where they don't want to go. Once you've pumped 3 sodiums out, there's already more out there. And as long as the pumps keep running, that concentration difference just keeps getting bigger. There's more and more and more sodium out and more potassium in. And that creates this really lopsided condition of way out of balance concentration and way out of balance electrical charges. And that's what your nerves rely on. But that's the way to work this. And unfortunately, the second you run out of ATP, these will shut down, which is what happens when your foot falls asleep. You cut off blood to your foot because you were sitting in a funny way, and you've deprived those body parts of oxygenated blood. And one of the first things to shut down are the sodium potassium pumps in your nerves. They shut down, your nerves stop functioning, and your foot goes numb. Now, there is another way of doing this. I did say that if the power goes out, you could have batteries on hand. Well, there is another option. You could use solar powered stuff. You could use a solar powered fan or something. You're harvesting one type of energy that is available, but that you don't need. And you're using that energy to pump something else that you do need. It's kind of the idea of a water wheel. If you're using a water wheel to lift a bucket or lift a box, what you want is lifting boxes. What you've got is flowing water. Flowing water is a form of energy, and you could capture it and then use the power you get from the water to turn a wheel and lift a bucket. The thing is that this only will work if the thing that is there for free is there at the time you need it. You cannot stockpile this. So it's typically, this is being done by molecules that are diffusing into the cell. So for example, here is a little glucose transporter. There's more sodium outside the cell because of the sodium potassium pump. It wants to come in. It can't come in through the membrane, but it can come in through this special little pump. As it flows in, it's the same idea as water flowing through the water wheel. The sodium flowing in generates energy that is enough to pump the glucose in. If you look, there's already more glucose in the cell. This is the high concentration. This is the low. You're pumping it from low to high, but you're using the energy that you collected from something that was flowing from high to low. The problem is that the first thing has to be in existence for the second thing to work. So if for some reason there isn't a high concentration of sodium outside, then this pump will not work. You can't make it work in any other way. You cannot use ATP with it. You can't stockpile any form of energy. And so this is relying on something that hopefully is always there, like a water wheel with the river always flowing underneath it or whatever. These are just the terms for the two different types of molecules. This that is pictured here is a symporter. Sym means same, anti means opposite. So in this case, the molecule that moves in to supply the energy also causes a molecule to be pumped in. So the things flowing in to give you the energy and the things that are pumped in are going in the same direction. You can have antiporters where you pump where something is flowing out to give you the energy to pump something in. That's all that matters. That's just all that means, is that, oh, it's a symporter if they both go the same way, and it's an antiporter if they go the other way. Doesn't change what's going on, but that's it. Okay. Everything that you were just looking at up to now was good for small stuff. You can make molecules, atoms, flow through channels. You cannot make entire bacteria flow through a channel. You cannot make entire chunks of, material flow through a channel. Sometimes your cells have the need to take in giant things, giant compared to molecules. A bacteria is not big, but it's enormous compared to an oxygen molecule. Okay. So if you need to get large stuff in, you need to get a little more active. You literally need to gobble it down. You need to gulp it down with the cell membrane. The cell membrane is movable, and it can literally, now this would be an example, this looks more like a white blood cell, and that would be like a bacteria that it's going to swallow, but it can literally wrap around it and swallow it, right? This also takes energy. So you're going to see these guys are going to be explained on the next page. This is taking stuff in, that's pumping stuff out. Transcytosis is basically combining the two. You're going to find that, for example, the cells that line your intestines, you've got little particles of food. You take them in one side of the cell through endocytosis, and you spit them out the other side through exocytosis. So it's just the combination of both of them. So in one door and out the other. Endocytosis is just bringing things in. There are times when there is a receptor. So when this thing bumps into a receptor, the cell suddenly gulps and swallows whatever's there. There are other times that the cell is just basically gulp, 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 gulp. That's just its thing. It's just doing it every couple of seconds constantly, or it's barfing the stuff out every couple of seconds in the form of exocytosis. Basically, imagine this is happening like soap bubbles. When you've got that little bubble wand and you blow air through it, initially you get this like bulge in the bubble film until eventually a bubble will pinch off and float away. That's exocytosis. And then like endocytosis would be the opposite, where a bubble would float up and it would merge with the bubble film and kind of become one again. But that's how it works, because the lipid membrane is kind of like bubble soap, I said. All of these require ATP. None of this stuff is free, but it's the only way to get big giant things into or out of the cell. Now, sometimes the big giant things that you're bringing into the cell are things you need to digest. So this is endocytosis right here. It forms this little dent until eventually the membrane pinches off and it traps these. Okay, we're going to talk about them as being food, right? So that's some kind of food molecule. Now that it's in there, it's just going to float around in the cell. This is a vacuole or vesicle. If you want to digest it, that's what lysosomes do. Lysosomes are bags full of digestive enzymes, and so what they do is a lysosome will merge with a vesicle, and all of the enzymes from it dump in there, and it digests that down to nothing. It can do this with food. This is also how your white blood cells kill bacteria. Okay, so that's the end of the active transport stuff.